In this video, we are going to explore the mean and variance of a statistical variable x, which is binomially distributed with n and p. Let us remember that n is a number of trials and p is a probability of success in a binomial experiment. You might want to pause and go back to see what are the conditions for an experiment to be binomial. We will need from your formula booklet the formula for the expected value of the variable x and the formula for the variance of x. So we are going to use this later. And in order to explore the mean and the variance, I chose a case where n is 20. You can follow the construction of my spreadsheet and do another one by yourself for another n. So first I take a probability p and I leave it at 0.15. I can change it later. And n equals 20. All possible values for x are 0, 1, 2, up to 20. So I generate all possible values of x. And I use an Excel formula that helps me calculate probability of x being x for a binomial experiment. So I know this formula with x, comma, n, and p. I need to know the order of the parameters as well. I need to add the word false because I'm trying to stop the video, okay? I need to add a word false because otherwise the cumulative probability will be calculated. False means that it's a probability distribution function. Now when I drag the formula, I see that I have an error. So why does it happen? Is that because when I drag the formula down, each of the values will be dragged down. Whereas I want to keep n and p as they are. I don't want to involve these values. N and p are constant. I just want to change x. Therefore, in Excel, if I put a $sign in front of the column and row of the variable, it will not change when I drag the formula down. So that's what I'm going to do. So see, I go back, I delete these ones, and I change. And for B2, I put a $sign in front of B and the $sign in front of 2, and same for this for the cell A, for P. And when I drag this formula down, I'll generate all the probabilities. So what I have here is, for example, this one is probability of x being 4 when n is 20 and p is 15, and so on. Probability of x being 10 is this one. So I generated them automatically to save some time. For the ones who have done their homework, you know how to generate all these by hand. And now I want to see the distribution to visualize it. So I'm going to construct a chart to visualize the distribution. These are probabilities of x being 0, 1, and so on. So I'm showing that if I change p, the distribution changes as well. If I change p, the distribution changes as well. Actually, p equals 0.5 will give me an interesting distribution. It's still here, p equals 0.5. This one didn't change yet. So that's for p equals 0.5. It's an interesting symmetric distribution. And if you think it should be like this, because the probability of success is the same as probability of failure. Now for p equals 0.9, when I'm going to start the video, the chart will update as well. So say that's for 0.9. When I put 15 by mistake, I see that I have an error because probability cannot be 15. So it's normal I get an error. So I went back and changed my mistake, putting 0.15. So now I want to check that all probabilities add up to 1. So if I add up all the probabilities, just another layer of checking that I'm correct. So see, all the probabilities add up to 1. And I'm going to start to calculate the expected value of your variable using this formula here. So I need to add the probability times the value. So see how in this cell I calculate the probability times the value. And then if I drag the formula for each cell, probability times the value be calculated. And then I add all these numbers and I get the expected value. So the expected value in this for these parameters is 3. Now I calculate the variance. Let us pause a bit to look at the variance. So to calculate the variance using this formula, I need to square each number. So square each x, multiply by the probability, and then add all numbers. After I add them all, I need to subtract the mean squared, and the mean, remember, was here. So I need to subtract 9. So I'm going to calculate this by multiplying the square of the value times the probability and then adding up all the cells. Times the probability, yeah, and then if I drag down, I'll generate for each row. So then I will add equals sum. All these values, I select them, and I subtract the E of x squared. Now, let me stop. I see I have an error, because a variance cannot be negative. So I reflect a bit, and I'm thinking, where is my error? So now I'm starting to look for my error. It was not intentional, but it's a good learning. So now I'm looking for my error. And I see that I multiply these two columns instead of these two. That's my x, that's a probability. Instead I took this value, so I'm changing it now. I delete, and I go for this value squared times the probability. Perfect, and now I need to drag the formula down, and this will update automatically. Yeah, so the variance is 2.55. I check again that I multiply the correct numbers. I check that I add correctly, and then I put my variance there. Okay, so what I'm doing next is that if you look in your textbook, they will say that the expected value is n times p. They give you that formula. And they'll tell you that the variance for the binomial is n times p times q, where q is a probability of failure. So I'm actually going to construct these two formulae here and check that they give me exactly the same answer as these two. So practically I make a case that the formulae that are given to you are correct because I check on some particular examples. That's not a correct formal full proof in mathematics, but at this stage you do not have all the mathematical tools required for you to carry the proof algebraically. So that's one way to check, and that's also a way for us to learn something about Excel and how helpful it is. So I'm starting to construct and make some space, and I'm starting to construct n times p because I am told in the book that the expected value of x is n times p. So I want to check this and see how when I construct it in this cell n times p, it's exactly the 3 here. So I highlight for you to see. And I'm also told that variance of x is n times p times q, which I'm constructing now. N times p times q. This is just text for us to remember what we construct. And here I put a formula equal n times p times, and I don't have q, but I know that it's 1 minus p. And see how these are equal. So now probably I'll change a bit the p to see that this keep the same. So when I change p, everything changes. These are the same. When I change again p, I make it very small. The graph changes. These are the same. And so on. So it's just a way to check that these formulae work. I'll leave it at 0.15. So from this we learn that for x, which is binomially distributed with np, these are the variance and the expected value for the distribution. Let us solve this question together. Please pause the movie and try the question by yourself. So x is the number of heads. Since I'm counting the number of heads, probability of success is probability of obtaining a head, which is 2 over 3. I repeat the experiment 4,050 times. It is a binomial experiment. It fulfills all 4 conditions of the binomial with n and p. This is my model. I always write my model. It's very important to point that it's binomial. And I know that for the binomial, e of x is n times p. So it's going to be 4,050 times 2 over 3. And I know that the variance of x is npq. I need to learn this by heart. So it's 4,050 times 2 over 3 times 1 over 3. So I do my calculation with a calculator and I get those numbers. Now I look again at the question to see if I answer it, and I notice that while this is my answer for A, in B I'm asked for the standard deviation. So the standard deviation is going to be square root of the variance, so my answer is going to be 30. This is a very interesting question that was posed to Pierre de Fermat in 1654 by a professional gambler who could not understand why he was losing. It inspired Fermat to set up probability as a rigorous mathematical discipline. So can you pause the movie and try to get the 2 mathematical models, the 2 binomial distributions to model this problem. For me, in the first case, rolling 3 dice in 4 throws, x, which is the number of sixes, rolling 3 sixes. X is binomially distributed with 4 throws. Probability of success is 1 over 6, because I have 6 outcomes. And I need probability of x being 3, which is going to be 4 combination 3, success to the power of 3, because I want 3 successes and I want a fail. The second model, rolling a 5 or 6 out of 6 throws, let's say y is number of 5s or 6s. Then y is binomially distributed, and I throw 6 times, so I repeat the experiment 6 times, and I'm interested in a 5 or a 6. So probability of success will be 2 out of 6. I can write it 1 over 3. And I'm interested in probability of y being 5, which is going to be 6 combination 5, probability of success to the power of 5, because I want 5 successes, and probability of a fail. When doing this with my calculator, I will get these numbers. So see how in this model, these numbers are still very small, but the second model gives a bit of a bigger chance of winning. But however, both of them has a very, very low probability of winning. We will now look into this example, and we'll find the expected value of this binomial distribution and the mode. May I remind you that with our previous formula, we found the mean, but not the mode. And the mode is the most often occurring value. So to find the mean, I will apply the formula. The expected value of y, or mean, is n times p. So it's going to be 4.8. Now let's find the mode. So to find the mode, I graphed the function corresponding to the probability distribution table. So the height of this bar, for example, is probability of x being 1, and the height of this bar is probability of x being 2, and so on, and this probability of x being 0, and so on. And as you see, and you saw from the previous simulation in Excel, that the values increase that the values increase and then decrease. So I'm practically asked to find the mode. One way to do it would be to generate all the values and see which one is the highest. Another one will be to look at the mean, and the mean is 4.8. Therefore, because this distribution is almost symmetric, not always, as you see, can be skewed on this side or skewed on this side, but I expect the mode to be around the mean somewhere. So I'm going to look at, I don't want to calculate all the values. It's a bit of a trial and improvement. So I'm going to look at probability of x being 4, probability of x being 5, because they are around 4.8. And then depending on which one is bigger, from my diagram probably is 5. If I see that 5 is bigger than 4, then I will go to calculate the next one as well to see that after it my graph is decreasing. If 4 is bigger, then I'm going to go and calculate probability of x being 3. So you are not going to have this in an exam, but it's just for us to visualize. So I'm going to calculate these two probabilities. As you see, probability of x being 5 is bigger. Therefore, I'm imagining that from x equals 4, my bar grows to x equals 5, and I want to see what happens for x equals 6. Is it still growing or is it less? And then I'm going to be sure which one is a mode. So I'm going to calculate probability of x being 6. So I get for it 0.177. Therefore, the mode is at x equals 5. This one is a mode, the most frequently occurring value, which is 0.227. So I use the mean just to estimate where about I'm looking for the mode, so that I don't calculate all the values from 0 to 12. We are going to try now this question, so I'm inviting you again to pause the movie and try the question by yourself. X is binomially distributed with 20 and p. Find variance of x in terms of p. So variance of x is going to be n, p, q, and q is 1 minus p, 1 minus probability of success. Find p such that the variance is the largest, so 20p brackets 1 minus p has a maximum value. So see how variance is actually a function of p. I can change p with x. No, better no, because x is used for something else. So it's a function of p, 20p brackets 1 minus p. So if I'm to graph this function, I see that it's a quadratic with one root being 0 and one root being 1, and it's a concave down parabola. Therefore, the maximum value will be here. This is the maximum value, and is for 1 over 2. So p equals 1 over 2, giving the maximum variance, and the variance in this case will be 20 times 1 over 2 times 1 minus 1 over 2. So it's going to be 5 over 2, or 2.5. So the maximum variance is when x is binomially distributed with 20 and a half, and variance of this variable is 2.5. And the last question we are going to solve today is this one. I'm inviting you again to pause the movie and try the question by yourself. X is a binomial variable where the number of trials is 4 and the probability of success is p. I don't know it yet. Find p such that probability of x equals 2 is 96 over 625. Right, so I need to replace what's probability of x equals 2? 4 combination 2, probability of success to the power of 2, probability of failure to the power of 4 minus 2. So it's 2. It's 96 over 625. So what I have now, it's an equation in p that I need to solve. Well, it's a quartic equation, p to the power of 4, but maybe I can do some tricks to be able to solve it. So let me first replace 4 combination 2. So 4 combination 2 is 4 factorial over 2 factorial times 2 factorial. You can also find it with your calculator. P squared 1 minus p squared equals 96 over 625. After cancelling, I get 3 times 4. I cancel 1 more 2, so I get 6. I divide everything by 6, so I get p squared brackets 1 minus p squared. 96 divided by 6 will give me 16 over 625. I don't rush to open the brackets because I'm going to get p to the power of 4. Rather, I will square all sides. So I will square root both sides. So what I'm going to have by square root is p brackets 1 minus p is 4 over 25. I can't, practically the solutions will be 4 over 25 or negative 4 over 25. But I can't have this solution because p is a probability, so it's positive. And now see how I turn it into a quadratic equation. So if I open the brackets, I get p minus p squared equals 4 over 25. I can multiply both sides by 25, so I get 25p squared minus 25p plus 4 equals 0. And then I'm going to apply the quadratic formula. And after I apply the quadratic formula, I'm going to get p equals 0.2 or p equals 0.8. I'm looking if both make sense. Yes, they represent probability, so they need to be between 0 and 1. So both of them are solutions to my problem. Therefore, I now know that if x is binomially distributed with 4, 0.2, or x is binomially distributed with 4, 0.8, then probability of x is 2 in both cases will be 96 over 625. You can check. So these two are going to be my answers. As you see in the last question, the concepts are the same, are exactly the same concept, but the last question is more difficult because it involves some algebra. This is, I would say, IGCSE algebra because it leads to a quadratic equation.